I hope you have all done your readings for this lecture. If you haven't, you may find some of the terminology unfamiliar and confusing. Quantum mechanics is a difficult subject, not least because there is still so much that we don't know. To start with, I'm going to go over the historical origins of the subject, focusing on Einstein, Podolsky and Rosen's 1935 paper, the EPR paradox, and the work of Erwin Schrödinger, who was the first to use the term entanglement, saying that he didn't see it as one of the characteristics but rather, the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Before this, it was often known as spooky action at a distance, a phrase coined by Einstein. However, it was later scientists who were able to experimentally test the ideas behind the EPR paper and Schrödinger's entanglement hypothesis. Friedman and Clauser in 1972 and Aspect in 1982 were some of the pioneering scientists who developed and ran experiments to test the ideas behind quantum mechanics, such as the violation of limits in the local realism theory first postulated by John Stuart Bell. So, what exactly is quantum entanglement? It is a physical phenomenon that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by a large distance. Instead, a quantum state must be described for the system as a whole. This means that you cannot describe a single particle, you can only describe what they are all doing together as a whole unit. Quantum systems can become entangled through various types of interactions, which I will talk about later. Entanglement is broken when the entangled particles decohere, or break up, through interaction with the environment, for example, when a measurement is made. Here is an example of entanglement: a subatomic particle decays into an entangled pair of other particles. The decay events obey the various conservation laws, and as a result, the measurement outcomes of one daughter particle must be highly correlated with the measurement outcomes of the other daughter particle, so that the total momenta, angular momenta, energy, and so forth remains roughly the same before and after this process. For instance, a spin 0 particle could decay into a pair of spin 1/2 particles. Since the total spin before and after this decay must be zero, conservation of angular momentum, whenever the first particle is measured to be spin up on some axis, the other, when measured on the same axis, is always found to be spin down. This is called the spin anti-correlated case, and if the prior probabilities for measuring each spin are equal, the pair is said to be in the singlet state. The special property of entanglement can be better observed if we separate the said two particles. Let's put one of them in the White House in Washington and the other in UC Berkeley. Think about this as a thought experiment, not an actual one. Now, if we measure a particular characteristic of one of these particles, say, for example, spin, get a result, and then measure the other particle using the same criterion, spin along the same axis, we find that the result of the measurement of the second particle will match, in a complementary sense, the result of the measurement of the first particle, in that they will be opposite in their values. The above result may or may not be perceived as surprising. A classical system would display the same property, and a hidden variable theory would certainly be required to do so, based on conservation of angular momentum in classical and quantum mechanics alike. The difference is that a classical system has definite values for all the observable measurements, while the quantum system does not. In a sense, the quantum system considered here seems to acquire a probability distribution for the outcome of a measurement of the spin along any axis of the other particle upon measurement of the first particle. This probability distribution is in general different from what it would be without measurement of the first particle. This may certainly be perceived as surprising in the case of spatially separated entangled particles. Now, before we go on to describe how particles can become entangled, are there any questions on this first section of the lecture?